Good morning, afternoon, evening, everyone, and a huge welcome to today's sessions. Quantum Advantage, are our algorithms ready? So today we're diving into a topic at the heart of quantum computing and its future, and that's whether our algorithms are truly prepared to deliver real-world advantage. Joining us are three brilliant minds. They've co-authored papers together and they work actively in the field. And I'm going to introduce the moderator of today's session before we kick things off. Herman Kolden is the CTO and co-founder of Aviant, a drone delivery company that started flying blood samples across Norway during the height of the pandemic and is now transforming logistics for remote communities across Europe. With a background in applied physics and training from MIT, Herman brings the worlds of research and real-world impact together, which makes him the perfect guide for today's conversation. So now I'm going to hand over to you, Herman, to introduce the rest of the panel and to kick things off. Thank you very much.
Thank you, Katie, and thanks for having us. I was particularly excited when I heard that Harry and Andrew had been invited to this fireside chat, because then I would get to reconnect with my former research colleagues. Because before I was doing drone delivery, my life path was quite different. I was headed straight into the quantum algorithms research world. And that's actually thanks to Harry and Andrew because of the paper we co-authored. Harry Krovi is a senior research staff member and manager at IBM, where he leads cutting-edge research in quantum computing and algorithms. And he has a background in both academic and industrial research, has worked on foundational quantum theory and practical quantum algorithm development. And before his role at IBM, he conducted research at Princeton and Raytheon, contributing to advancements in quantum technologies that bridge the gap between theoretical and real-world applications. And maybe, Harry, you can just tell us briefly what you're working on these days.
Yeah, sure. And thanks for having me here. Yeah, so in IBM, which I joined only in Jan of this year, so it's only been a few months, I'm currently continuing work on differential equations, actually in collaboration with Andrew and a few others. And I've also gotten back into something that I had worked on a while back, which is quantum algorithms for algebraic problems. Nothing specific yet, but we're exploring some of those techniques which we think might be useful. So yeah, broadly these two.
Yeah, super. And Andrew is a professor in the Department of Computer Science at the University of Maryland. He was a co-director of QUIX from 2014 to 24, and is the director of the NSF Quantum Leap Challenge Institute for Robust Quantum Simulation. Quite the name. His research interests are in the theory of quantum information processing, especially algorithms. He has explored the computational power of quantum walks with one example of exponential speedup. And he's also developed fast algorithms for simulating Hamiltonian dynamics. And other areas include quantum query complexity and algorithms for algebraic problems, which Harry mentioned. Yeah, maybe you can tell us a little about your work, Andrew.
Sure. Yeah. Thanks very much for the opportunity to be here. I'm looking forward to the conversation. Yeah, as Harry mentioned, we have a collaboration on, thinking about the limitations of quantum algorithms for differential equations. I also have some other work thinking about, potential applications of those kinds of algorithms. I've thought a lot about quantum simulation, as you mentioned, over the years, and my group is continuing to think about faster algorithms for quantum simulation. We're also really trying to think about use cases for quantum simulation algorithms to things like nuclear physics and other kinds of areas. I have some ongoing work in questions related to quantum query complexity, which you also mentioned in your introduction. I'm also interested in sort of quantum computing under locality constraints, kind of how information can move around quantum systems when there are constraints on the interactions between different parts of the system. So yeah, I think there's a lot of, one of the things that I like about quantum computing is it's many different things, and there's lots of different interesting kinds of questions you can ask. So things are going in a lot of directions.
Exactly. And I think that's a good place to start this conversation, because we're in the realm of differential equations on quantum computers. And I remember when we were working on our algorithm, we focused on one aspect of that, sort of the middle part, where we made a lot of assumptions about how does the data get in and how do you use the result. But when we then think about the question of this fireside chat, which is, are our algorithms ready? I think a good place to start is to ask, what should they be ready for? What is sort of it's not just about finding some neat mathematical formula. In the end, we want to use these quantum computers for something. So if you were to try to describe sort of the mission in your work, based on your work, what do you actually hope they will be used for?
Yeah, well, I mean, maybe just to jump all the way to the end to the big question, I think the answer is no. Like our algorithms are not ready. There's a lot to figure out about sort of how we can hope to use I mean, specifically in the context of differential equations, right? I mean, we know very specifically we want to say, break, RSA with quantum computers, like we know very specifically what that would mean, what it is we would have to do. But, in terms of how we would use quantum computers for problems related to differential equations, it's not so clear, right? I mean, I think that the hope, or at least my hope, is that, maybe there are some kinds of problems where you can describe them in a way that you can actually get the input into the quantum algorithm for differential equations, and you can find some interesting properties of the solution of some big system of differential equations that you can efficiently extract from the kind of representation of the solution that quantum algorithms are able to produce, and that will allow you to solve some problem of practical interest. But really making that concrete and sort of like identifying problems where it seems like there's a compelling case that there's some question which would be hard to get the answer to with a classical computer, and that you could get out in this way with a quantum algorithm, is actually not so easy. And I think that this is, for me, this is like a bit of a gap in the field to understand what those applications would be.
Right. So do I understand correctly that the goal is sort of to be able to operate in a way that we today use classical computers for simulation, but much faster on a quantum computer? Or is sort of the entire purpose of a quantum algorithm different in its operation?
I mean, I guess the hope is that we could operate in the same way, and that we have some question we want to answer. We somehow model the system of interest, on a quantum computer, and then we get the answer that we're looking for, right? But there are things that are, if we talk specifically in the context of quantum algorithms for differential equations, there are the kind of proposals for addressing those kinds of problems with quantum computers involve representing the information about the solution of the differential equation in a really different way than you would on a classical computer, right? So in a classical computer, you would have like an explicit representation of kind of the state of the system at any given time. You could sort of evolve it forward in time to find out what the state of the system is, maybe at some later time, and you have a full description of that in the memory of your computer. You can go in and you can inspect kind of any piece of it, however you like. But the way we can potentially get a significant speed up from trying to use quantum computers to get information about systems of differential equations involves representing that state of the system as a quantum mechanical state. And that's something where you can't like directly access all the information about what is the entire state. You have to make a quantum measurement that reveals some information about the state. It's not the same kind of thing as really having an explicit description of the entire state. And so this is why, while I think in terms of like the end-to-end, behavior, what we would like to have is, the same kind of way of operating as we do with kind of classical high performance computing, in that, you have some problem you want to solve, you describe the problem, you get some answer out. We would like to be able to do that kind of thing with the quantum algorithms for differential equations. But in terms of the details, like, actually getting there will depend on the nature of the problem, the question that you want to ask about the solution. It presumably will not be the case that sort of just anything you could pose to kind of classical methods for, differential equations. I don't know, finite element analysis, or the kinds of approaches people take to solving systems of differential equations on classical computers, that you would be able to do everything with exactly the same sort of kind of process for setting things up and getting information out of the solution as you would classically. Presumably, the details will be quite different.
Yeah, so maybe I can jump in here. Like, I think, so I agree with what Andrew was saying. I think maybe I can say it in a slightly different way, which is that, when we're trying to find a usefulness for quantum algorithm, or even like a whole field of differential equations, we have to kind of satisfy three different things, right? Which makes it hard to find these algorithms. One of them is, you want it to be quantumly efficient. You want it to be classically hard. Otherwise, there's no much point in using a quantum algorithm, right? So, and then you want it to be useful as well. Like you want it to have, like some kind of utility, right? So one use case is looking at, like, for example, where classical algorithms for differential equations are used currently. Like in national labs, people apply these, solvers for lots of different important problems. So, seeing if there's a quantum speed up when you go all the way from end to end, like we were just discussing, right? Not just prepare the quantum state that has all the amplitudes in quantum memory in a sense, but like actually producing or extracting a classical, quantity that's of interest. So when you take into account this whole thing, is there a quantum speed up or not? And how much is there? And is the speed up actually there in a regime of interest? Like maybe that nonlinearity is somewhat high for those problems or something like that. The answers to these questions we don't currently know. So in that sense, we're not ready. But I would also say that the differential equation, quantum algorithms of differential equations is somewhat new. Maybe our paper is already somewhat old, but it's the first of its kind, right? Like in 2021 or whenever we wrote this. Since then, there's been a lot of progress, but still, I think, yeah, there's a lot more to be discovered. Yeah.
And if let's focus on that first part, because it's sort of almost banal how we cannot even load the quantum computer with the information we want to solve. And so I'd love to understand, maybe you can explain to the audience, like, why is that? It sounds simple, you just input it, right? It's like why is that hard, and what's been the progress the last time?
I mean, I wouldn't say it's hard in the sense that if you ask for a lot, like, load arbitrary amounts of data, like a matrix that has arbitrary entries with no sparsity structure or something like that, that's hard. But that's typically not the case. In differential equations, you have matrices that look kind of like band diagonal, for example, or have some other kind of sparsity structure. And for sparse matrices, especially when the sparse entry can be calculated efficiently. So if you just say, what is the ijth entry, then if there's a classical algorithm that can quickly find out what it is, maybe there's a formula for it. In fact, one of the papers that we wrote on plasma physics with people at MIT, that one had a formula for each entry, which is, in the sparse matrix. In that case, there are well-known, techniques called block encoding techniques, which can encode this or load the data into a quantum computer. But is this enough? Like, does this cover all the interesting and important cases? Probably not, because sometimes you have dense matrices, but still with some structure. I mean, one simple example is the Fourier matrix, right? It is unitary, it doesn't have to be block encoded exactly. It's completely dense, but it's got an efficient algorithm to encode it, right? But that's just one example. But maybe there are others that have some, entries all over the place, but have, some nice structure that comes from the physics of the problem. So developing quantum algorithms for these kinds of problems, these kinds of matrices, to load these matrices would be useful. I think there's been progress, but maybe there's more to be done, because we're looking at a current problem right now, and there is no block encoding technique that seems to apply to it. So yeah, so we still need more algorithms.
Yeah, maybe I can just add that I think that it's quite plausible that you can sort of efficiently prepare the initial states that you need, and also realize the kind of matrices that you need to describe the dynamics of systems of differential equations, when you have some kind of nice implicit description of the system, right? So when the system that you're talking about is described by some formula, like Arya was saying, you have a formula for the entries of the matrix, or you have some formula that describes the kind of the form of the initial condition. There may be cases where you're interested in solving differential equations that describe the dynamics of some initial configuration that's just given to you by explicit data. It's loaded onto your hard drive, right? It's a lot of kind of explicit information, and that's the kind of situation where it's not so clear how you would actually from that kind of representation, it's not so clear how to sort of load this this kind of like classical description of a quantum state into an actual copy of the quantum state, right? So when you have like an implicitly represented system that you kind of understand in some abstract way, then it seems like it certainly depends on the details, but probably in many cases, you can actually try to run the kinds of quantum algorithms that we have for differential equations, but they really do not seem kind of well suited to like handling processing of explicit data that's like provided, that's written down on a piece of paper, or that's, loaded into the memory of your computer. Then we kind of don't expect to get the kind of exponential advantage, the exponential savings in, at least in space, that it takes to represent the description of the system, in the quantum memory as opposed to in a classical description.
And then to wrap up sort of the input loading part, can you be a little explicit about, is there anything we know will not be possible? And is there anything where we have seen a very interesting example that, might be both quantumly efficient, classically hard, and useful on the input loading side?
The input loading. I mean, I think it maybe depends on the assumptions, right? So, there's this model that's often discussed of what's called quantum RAM, right? If you have your input data stored in a kind of quantumly accessible memory, then maybe in that setting you can actually prepare quantum states from this kind of quantum RAM description of the system. But there's a lot of, I don't know, like uncertainty about whether that's a realistic model to imagine that you could actually build this kind of quantum accessible memory. It's probably not so realistic. So I think it maybe depends a little bit on the assumptions one is willing to make and what it's possible to actually realize in practice, about these different sort of like input models.
Yeah, I agree. I mean, I think, like I don't know if any no-go results exactly, but it should be not so hard to show that something like a very dense matrix that's exponentially big, where the entries are somewhat arbitrary, where there's no structure or something like that. It should not be that easy to load that information into a quantum computer. So we're hoping that if it's explicit, then it's either sparse or has some structure in some sense, or if it's dense, then has some physics that you can exploit or something like that.
Okay, and to be clear, so there is no Nogo theorem which proves that you cannot load, let's say, the shape of an airplane or a drone. There are, on the input loading side, there aren't any known no-go theorems?
I mean, I think like a simple kind of counting argument will show you that you can't prepare general quantum states efficiently, right? If you want to prepare a general state of an n-qubit system, then you're going to need a circuit of size that's like exponential in n, but a state that describes something related to the shape of an airplane wing, is not a general configuration, right? It has some structure. Like, we build airplane wings in particular ways because they fly well. I mean, so that's, I think that relates to what we were talking about, kind of with implicit specifications of input data or descriptions of how the dynamics work in the system. If you're designing an airplane wing, maybe you have a description of the curve that shows you how it's going to be shaped, and maybe you're trying to design it, so you're trying to consider variations of that shape, but you parameterize the shape with some small number of parameters. But then maybe you want to simulate some differential equations that describe, I don't know, the flow over the wing, or some property of the radar cross section of the wing or something like this. And you need maybe very high resolution to get an accurate representation of what's going on. So you maybe want to be able to discretize the system very finely. But you can do that from this kind of like description of the geometry in terms of just a few parameters. That would be the hope.
Exactly. And let's now assume that we managed to do this. We found some nice ways, of course, some nice problems to load them into the quantum RAM. And now the question is about, doing some calculation on them. So assuming that we had the hardware there and we had the initial state, what do you think are sort of the most interesting and hopeful recent developments on the differential equation side?
I mean, I would say like differential equations for linear differential equations have progressed quite a bit, and like I think we have a good understanding of when they are efficient, and what we can hope to get, aside from the data loading that we just discussed, after it's been loaded, to get the quantum state in the end, again without talking about what can be measured efficiently. This I think we kind of understand, although more kind of like reducing the gate counts and those kinds of things can happen, of course, like for example the way it's happening with factoring, where even bringing down the number of qubits required, takes a lot of effort beyond a certain point, right? So things like that can be improved for sure. But then in the nonlinear regime, I think we're pretty much where I guess, our paper left it off, right? I mean, there've been a few papers that showed with different techniques, we get somewhat similar, results. But for general nonlinear equations, it seems like it's not possible. In fact, we have a Nogo result in our paper that talked about how, for even mildly larger nonlinearities than what we showed is not possible.
Right. And maybe you can briefly summarize what the result of our paper was.
Oh, yeah, I'm sorry. Yeah. So, we defined this quantity called R, we don't want to get into the details, but essentially what we said was there's this, nonlinear, the strength of nonlinearity, and then there's the dissipation, which kind of counterbalances it in a sense. And what we said essentially is that when the nonlinearity is weaker than the dissipation, then we have an efficient algorithm. But when the nonlinearity is larger than the dissipation, in fact, we said it's larger than square root 2 times dissipation, which was improved and all that. But still, when the nonlinearity becomes large, we have like a counterexample which showed that the quantum algorithm cannot prepare states like that, right? Which we needed in our algorithm. So I guess one way to look at it is that we looked at very arbitrary nonlinear differential equations. Well, very, like in the sense that there's polynomial nonlinearity, right? But if you now ask, well, that's very general. What about like reducing it down to maybe some special cases? In fact, the field of computational fluid dynamics, people spend their careers mostly on a differential equation with a name like Navier-Stokes or Vlasov equation or like maybe the Black-Scholes equation or something like that, right? So these are very specific differential equations with just a few parameters. Is it possible to do something better for these, maybe with some regimes of these parameters? That kind of question would be interesting to look at. Yeah, but yeah, Andrews have worked on some recent, improvements to the differential equations for linear systems like LCHS and stuff, will definitely help with like these nonlinear differential equations, because as you guys may have read seen, it's nonlinear differential equations are converted to linear differential equations, like in a bigger matrix or bigger space, and then solved, right? So yeah, we'll have to see how we can do that more efficiently for higher nonlinearities for these specific equations.
Yeah, I guess as you said, we have this no-go result that says that for general classes of nonlinear differential equations, we can't expect the algorithms to be efficient. So really, if we want to get significant improvements, they would have to take particular features of differential equations into account. But there's obviously a lot of scope to do that, to look at some specific class of equations that's has some nice properties, and really zoom in and try to get better algorithms for particular cases. That's not really something that I've thought about, but it's definitely a good problem to work on.
So it comes back to what you said, Harry, about we're looking for quantum algorithms that are quantumly efficient, classically hard and useful, and in fluid dynamics, the nonlinear, for example, Navier-Stokes and so on, they're definitely classically hard and useful, and we show that we have a quantumly efficient algorithm if it's just a little hard, but not very hard. But then it's almost depressing to hear that there hasn't really been a lot of progress. Like, is that really the case? Is there no shiny light in the distance for solving Navier-Stokes in general or something?
Well, I mean, we don't know if it's even possible, right? I mean, one thing Andrew and I and with some others are thinking about is, can we extend the no-go results that we have in the PNAS paper that we were just talking about, which I just described, like, where when the nonlinearity becomes large, we cannot hope to solve these problems efficiently. But the no-go result was based on a problem that's a very toy problem, like it was not useful in some sense. But can we extend those results to like somewhat more useful or more practical problems? That would be interesting. We don't know. So that viewing it from that side would be good, but also taking specific examples of differential equations. Yeah, I mean, that would be nice too. Maybe before jumping to something like Navier-Stokes, taking like, the 1D version, the Viscous-Burger equation, or even like more specialized equations. Like in my recent paper, I was looking at this thing called the Riccati equation, which can be linearized exactly in a higher dimension. So in that sense, you might say it's already linear. But still, it's not all clear how to solve it. But it is written as a nonlinear differential equation. And it turns out that when you do linearize it that way, block encoding is not obvious. And also, by taking into account the constraints of solving linear differential equations, you will get some condition on the strength of the nonlinearity. So it turns out that you can kind of solve that problem, but not to arbitrary nonlinearity, even though it can be linearized. So looking at specific examples like that might show the light, as you were saying, like, maybe take us towards Navier-Stokes. But maybe Andrew has I don't know, different approach to this.
I mean, my general feeling is that, I'm like not very optimistic about quantum computers giving significant advantage for nonlinear differential equations. I think the challenge in general is that nonlinear dynamics have this, kind of the hallmark of nonlinear dynamics is just the kind of property that you can have states that are initially very close that kind of become very far away, rapidly when the dynamics run, right? That's something that kind of, things can spread a lot faster when you have nonlinearities in your differential equation. And this is, something that this is an effect that you can like, leverage to solve hard problems if you can follow the dynamics. And so you can, this is how the kind of the Nogo results go, right? That they sort of show that if you would be able to follow the nonlinear dynamics with your quantum algorithm, then you could sort of use that to solve a problem that is hard, a problem about distinguishing quantum states that should be very hard to distinguish. And so that's how sort of our Nogo result goes in this toy example that Hari mentioned. And I guess the question is, if you look at some specific class of nonlinearities, can you sort of prevent this from happening? Can you sort of show that in some application? Because I think generically, like if this happens, if you look at dynamics that have this property that they can take states that are very close to each other and kind of pry them apart so they become very distinguishable, then you can use that to give a no-go result, and you can show that you won't be able to give fast quantum algorithms for such cases. So, can you identify that feature in the kinds of nonlinear differential equations that people care about for applications, for fluid dynamics or, other kinds of systems? And my guess would be that the answer is yes, but it's obviously, when you impose more structure, it's harder to identify that feature and sort of show that happens. So yeah, I mean, I'm not incredibly optimistic about sort of this direction of kind of, looking at problems that are hard classically because of the nonlinearity, and then sort of, alleviating that by having a quantum algorithm. It would be great to find such a case, but in our work, as you mentioned, like very specifically, we have to look in this regime where the nonlinearity is weak, basically to not allow for this kind of phenomenon to happen. And I think it's already quite interesting that you can find this kind of regime where really there is a nonlinearity and it's acting and it's doing something non-trivial. It's somehow kept in check by some dissipation, but it's and I think it's it's maybe nice to maybe try to identify regimes where that kind of thing happens and there's some maybe practically relevant problem. Like, I don't know what this would be, but maybe where there's some problem where this would actually be a useful tool. I think there's maybe some scope for that, and that would be really nice. But somehow going like deep into the nonlinear regime and sort of hoping that there would be kind of quantum advantage there, I'm not very optimistic about. I would love to be wrong.
Right, yeah. It's interesting you said that you're skeptical about the problems where the classical hardness is due to nonlinearity. So we're looking for somewhere where the classical hardness is for some other reason than nonlinearity. And then let's assume, okay, let's step away from nonlinearity for a while. We found some other problem where we could load it into quantum RAM. The problem is classically hard for, let's say, the dimension or something, not the nonlinearity. And then it comes down to, okay, now we want an answer. We want a number on the pressure under the wing or something. And then you just sit there with this quantum state and like you don't know what to do with it because you can't look at it. And that's the final piece of the puzzle that we just said in our paper. Somebody else has to fix that. What are the most interesting developments there?
Well, so I think, people did look at some in fact, citing this paper that we wrote, there were quite a few papers that looked at like the Vlasov equation and even CFD that I came across, showing basically working out what it would mean to use that algorithm for that application and showing what this quantity r less than 1 would mean in using, in terms of the physics of that problem. So it's kind of interesting that all this has been done and worked out. So, I mean, I would say in these papers, people were actually trying to come up with a classical quantity that can be extracted from the final state. But one thing to mention about that is when taking into account the speed up over the whole thing, you might find that, like, in fact, in our paper, we had an exponential speed up in the dimension of these matrices, right? When r is less than 1, when the nonlinearity was small. But it might be that the dimension is kind of artificial in the sense that the physics of the problem, like it could be just 3-dimensional, right? But the higher dimensional matrices come because we imposed a very fine grid on it, right? So getting a exponential speed up in the dimension still doesn't mean anything because the dimension is related to the accuracy with which you want some quantity. And in the end, when you extract that quantity from the quantum state, the accuracy is usually, 1 over the epsilon, the error to which you want this. And in the end, epsilon is the only quantity you have in the whole problem. So you might only get a polynomial or even a square root speed up over classical algorithms, despite getting an exponential speed up in the grid size to prepare the quantum state. So this extraction of the classical quantity is kind of important because that's where you could lose all the speed up. And when there are not enough parameters, that's usually what ends up happening too.
Yeah, I remember that. It's sort of like having a good algorithm which can spend a lot of computing power on precisely measuring like how long a pencil is or something. And you can measure it more and more precisely, but it doesn't matter. And you can make it harder and harder, but it doesn't really matter. So you should like find a problem that's actually where it really, really matters to have these high dimensions. And
Yeah, I mean, a problem that has a natural higher dimension is useful because one example where you might, question how useful it is, but like the recent paper that Google had, and I also had a follow-up paper on this, on coupled oscillators, right? You have exponentially many, oscillator the masses that are, connected by springs, and there's some sparsity structure there, and you set it into motion, and you want to know what the I guess one question is what the energy in some subset of these things is, some kinetic energy, for example. This could model like various things like molecules maybe and other things. So there's some usefulness here, but I guess there was some questions about like how useful is it really practically. But still, if you set aside that, I think, one thing you can say is that the dimension here is not artificial. The number of masses is physical, so there's actual, very high dimensionality to this problem, and the exponential speed up in that is real. So, in fact, they do talk about like an end-to-end problem here, right? So problems like this, where the dimension of the problem comes from the physics of the problem, are useful because then you can try to get an exponential speed up there. But if it comes from like an imposed grid or something, it's unlikely that that exponential speed up will remain when you go all the way to a classical quantity.
Yeah, I mean, I'd say probably the most obvious and maybe the most compelling, instance of such a thing is quantum mechanics, right? I mean, quantum mechanics is simulating quantum mechanics, is a problem about differential equations, right? I mean, the problem is the Schrodinger equation. You have a Hamiltonian that describes the dynamics of the system, and you just very naturally have this high dimensionality of a, quantum mechanical system, right? I mean, it's everything, and also you have very natural observables that you might want to measure to describe the physics of the system. So that's, I think that's the kind of the case where, I mean, you may choose to categorize things, where quantum simulation is a different thing from kind of quantum algorithms for differential equations, but I would say, it's kind of in the same category, right? Simulating quantum mechanics is really, simulating the dynamics of quantum systems is really about understanding the solutions of systems of differential equations. And so that's maybe like a good case to look at to understand where it is that we really have a compelling case for speed up, right? We know that problems about simulating the dynamics of quantum systems are as hard as anything a quantum computer can do, right? So if there's any quantum advantage anywhere in quantum computing, it's in quantum simulation. It's also, by the way, in these, systems of coupled, masses with springs that Hari was just mentioning, that kind of problem also has that. sort of property. So, we have these kinds of instances where we really do have, pretty good evidence for quantum advantage, that there's something you can do with a quantum computer that's not doable classically, even in an end-to-end fashion, where we talk about, include the task of preparing the initial state and measuring some information at the output. The challenge, I guess, is to really find that in, concrete applications, and maybe, in concrete applications that go beyond, merely simulating quantum mechanics. But, simulating quantum mechanics, I mean, I think that's really a very good potential application of quantum computers, which is, yeah, I mean, I would argue it should be in the scope of this discussion.
Right. Yeah, it's true. I guess that I feel like people expect more from quantum computers than just simulating quantum mechanics, but I agree, like it's a natural application. But then, so far we've talked about, okay, it's hard to load the input in the first place. It's hard to then simulate something where the problem is interesting for the right reason, and then it's hard to read the output. If you could solve like one of these three phases, like you're guaranteed like for some interesting application, like boom, solved. Because it sounds like we don't have any of those right now, maybe. Like which of those do you hope to discover in your work that you solve or prove is impossible?
I'm not sure that I understand the question exactly. I mean, I think we have, in some contexts, we have an understanding of how to do all of these things, like under some assumption. I think the challenge is really to like put them together in the context of some concrete application. And I think, yeah, I don't know. I mean, I think you really can't take these problems. If you really want to think about applications where you're actually getting something, useful out of the quantum computation, you sort of have to consider them all together. You need all of these things. So I'm not sure that I would be, happy somehow, in some really concrete application, understanding how to do only one of these things. I mean, somehow if you can't really make it end to end, what's the point?
Yeah. So, I mean, I would, the reason, like, in our paper too, we focus on the middle part is that it's kind of more general, right? I mean, you don't need to know about a particular application. Whereas the ends, like loading the data and unloading it, depend on the particular application. Like the matrices, like in the Blasov equation, solving Blasov equation look different from like CFD or some other application, right? So after you develop the algorithm in the middle, where you take some initial quantum state that's been prepared for you and data has been loaded, and then you solve the equation and prepare the final quantum state, this algorithm can be looked at separately, and we can improve it and make it like with some assumptions or something like that, make it more efficient and things like that, right? And now it's ready to be applied to a particular application. So you can take now a particular application like CFD or something, and then talk about how you can load the data without losing the speed up, and how you can unload the data without losing the speed up. And then, that kind of approach, I think, makes sense, which I think people are taking right now with like applying these algorithms to different applications. But I think one thing to think about is maybe there is some meaning, some advantage to looking at the whole thing at once, in some sense. Because if you take a particular application, you might find that there are some assumptions about the problem that come from the application that help the middle part as well. I mean, it's not clear what they are and how to use them, but yeah, it might help to look at the whole thing and try to, improve on all of them. But that has to be done. I think this is the progress that we were talking about earlier that we need to do.
And do you feel like this is the direction the field is headed, or are we still stuck in trying to solve the general classical mindset parts?
Well, I think people are looking at both. Yeah, certainly there's a whole group of people looking at applications, like specific applications for sure. And there are many who are improving these algorithms. But I would say the big hurdle of crossing this nonlinearity r less than 1 thing that we were talking about has not yet been done in a meaningful way. Maybe there are some specific examples where people were able to show something or the other, but yeah, I would say that's like a big hurdle.
Yeah, I agree.
Yeah, all right. Then I think we're ready for some Discord questions. One question that I wonder a lot about is, I often hear talk about quantum machine learning, and my hype red alarms go up, and I feel like it's too hypey to be useful. And in the end, then they're talking about the linear part of that usually, because that's what's more feasible on a quantum computer. Do you have hopes for that field, or are you worried that it sounds good, but it's not useful in the sense that we have talked about and like suitable?
Well, I'm not even sure that it sounds good. I'm very I'm very much on the skeptical end of things. I think a lot of the success of classical machine learning is about explicit input data, and we talked about how that can really be a challenge for quantum algorithms. Yeah, I think there's really at least for my taste, not really good evidence for the potential of significant speedups from quantum computers for machine learning problems. And I think, it would be great to find new applications in that space, but I think, we should be, I think for me, like my prior, if I just take some problem out of thin air, my prior about whether there will be a quantum speedup for that problem is no, right? I mean, there has to be some really, special thing about that problem that makes it amenable to speed up with a quantum computer. It's not, you can't just take some random problem and like hope that there's going to be quantum speed up. So there should be a reason. And for me, like these, kind of machine learning problems, there's not great evidence for it being likely that you can get quantum speed up. And maybe there's even evidence in the other direction from these kind of dequantization results that have been found.
Yeah. Yeah, I mean, I agree. I mean, I haven't worked actively on machine learning myself, so I only have like an outsider's perspective here. So mostly is what Andrew was saying too, that I think where people have shown some speed ups might be where it was kind of cast as machine learning rather than where it being inherently, that.
Right. So, good old linear algebra.
Yeah. But one thing to mention is that machine learning in the context of learning quantum states and quantum aspects of quantum processes, for example, has had some recent progress and there's some interest in there, which I think is interesting. It may not be traditional machine learning like classical machine learning, but in the quantum context, we have to define what learning a quantum state really means. And I think in that there's been nice progress recently.
Okay.
Yeah.
Now we have some Discord questions rolling in here. So Arthur in New York City says, since you refer to coupled oscillators, have you looked at simulating the dynamics of a non-local Heisenberg Hamiltonian?
I have not. My follow-up paper to that one just looks at somewhat more realistic scenario of coupled oscillators with damping. And that's also the paper where I worked on the Riccati equation, like I mentioned, which involves control theory. But coupled oscillators with nonlinearity, I don't know if that can be done easily.
Yeah, I guess the question was about something about non-local.
Yes, simulating the dynamics of a local Heisenberg Hamiltonian.
Yeah, I'm not sure exactly what model the question is about. I mean, in some of my work on, just quantum algorithms for simulating Hamiltonian dynamics, I guess the question is about, simulating quantum mechanics. We've looked at kind of one-dimensional Heisenberg models with local interactions as like a really basic kind of simple model to kind of, have a scenario where we can look at what is the cost of simulating quantum dynamics in a system where we kind of have some reason to believe that would be a hard thing to do classically. That's definitely like a kind of a test case that we've looked at a lot. I guess I haven't looked specifically at, maybe, I guess there is some work on sort of the cost of simulating the dynamics of these models with power law decaying interactions, where you actually do have, in some sense, non-local interactions, like you have Heisenberg couplings between spins at long distance that decay with some power law. So there is some work on that.
All right, now a question from James, also in NYC. And he's asking, what are some examples, if any, of classical differential equations that admit quantum enough descriptions to be amenable to attack on differential equations via quantum algorithms? So I guess he's asking about when we look in the area of simulating classical differential equations, what are some of the most, we mentioned previously the Burgers equation, with the viscous Burgers equation. What are some of the other sort of maybe quantum-ish attackable problems?
Yeah, I guess people have looked at things like electromagnetic scattering, like that's one scenario that people have looked at. So there are also these models that come from fluid dynamics that we were talking about. I think, in some of those problems, a potential limitation that I think Hari was discussing before is that, when you have systems in kind of low spatial dimension, there may be some reasons to think that, perhaps it'll be difficult to get more than a polynomial speed up from quantum algorithms for differential equations. So, maybe a more compelling set of problems could come from something that's not limited to sort of low spatial dimension, and where you have a sort of like more highly connected system. I'm not sure exactly what that is.
Yeah, I mean, I don't know good examples, but like anything that has many particles interacting, for example, where the interaction is local, meaning so you'll get some kind of sparsity constraints from there. But yeah, what cases these are, what applications these are, I'm not 100% sure.
Yeah, I think that's an interesting point too, is that, I mean, in the end, even classical mechanics is at least usually mostly linear. Like Newton's laws, they're linear laws. And when you look at fluid dynamics, the way you derive Navier-Stokes, you start by looking at particles, but at some point you average over all of them, and then you get some nonlinearity. So I also wonder if that's an interesting approach. Maybe since quantum computers are good at linear things, maybe going the particle direction is good, because then you have a lot of particles. And I remember there was some work, it was called Boltzmann lattice equations or something. But yeah.
Lattice-Boltzmann equations are like exactly things like this, which put things from continuous to a lattice, and there are high dimensionality and things like that. But ultimately these are still models for the actual thing that you want, which is the fluid. But if you think of this as the basic model, then yes, you can again try to get an exponential speed up in the dimension, which is again fixed, right? Not fixed, sorry, given to you. But but if you think of it as a model, then that dimension depends on how well you're trying to model the fluid. So I guess it's a question of which comes first. Yeah, but there may be other systems too where there's a natural, high dimensionality, like gravitational systems. There's been no work on that, for example. Is it possible to simulate them better than classical techniques? It's not clear. Also, just particles with elastic collisions. If it's elastic, then the energy is not lost, and this is very likely to be simulated by Hamiltonian simulation, but still the physics is slightly different. It's not quantum. Things like this. I mean, you could have, examples like this. But again, when we prepare things like this, I'm sorry, when we come up with not toy problems, but come up with problems like this, we have to try to relate it to something actually useful. But to develop new algorithms, it might help to just come up with a problem and solve it, and then see where it's applicable.
Yeah, it almost reminds me, since I lead obviously the technical team in our drone company, and there's an analogy between making nice technical solutions, and then the business team comes and say, hey, how does the customer really notice this? And you need to start there. So it's always interesting to work on the subcomponents, but in the end you have to go like from step to step. How does the customer experience start, and how does it end?
Yeah.
Yeah, I think one of the challenges in
quantum algorithms. Oh, sorry.
Go ahead.
I was just going to say that thankfully in quantum algorithms, there's no customer experience currently as another constraint. But yeah, that would make things more difficult.
Well, but I guess maybe if we take maybe less immediately sort of economic kind of perspective, right? I mean, our customers could be sort of people in sort of application areas that could potentially benefit from quantum computing, right? People who want to do computational fluid dynamics, or who want to do, I don't know, some other kind of computational physics or engineering, and they want to know, kind of can quantum computers help with the chemistry, or there's lots of areas where we might hope to apply quantum computers. And I think one of the challenges is that there's sort of a disconnect between sort of the information you need to understand to know how to design quantum algorithms and think about building quantum computers, and the like specialized domain expertise that people have in computational quantum chemistry. There's not so many people that are kind of bridging these worlds. There are some, but I think this is one of the challenges of sort of like sort of having quantum algorithms people sort of talk to people who know about what are the problems that potentially we can solve with quantum computers. And I think having more kind of dialogue between sort of people who have specialized knowledge in these sort of different areas, obviously will happen over time. But the more of that we can have, maybe the more applications we'll find for quantum computers.
Yeah, and that's why it's good that we have things like Womanium and Wiser who do bridge the gap. Unless all of the audience are quantum algorithm designers and there are no customers here for us to teach about it. I think that's a good way of wrapping it up. I don't know, Katie, anything to add?
Oh, can you guys hear me okay?
Yes.
Yes.
Yes, absolutely brilliant talk. I thoroughly enjoyed it. From what I'm seeing on Discord, I think everyone else did. Thank you for such an incredible panel. Andrew, Hari, Herman, it was really insightful and thought-provoking. And you touched on kind of several technical challenges, which we're actually covering next week. So thank you for setting us up for next week in such a beautiful way.
Well, thanks for the chance to be here.
Yeah, thanks for having us.
Have a really lovely rest of your day.
Likewise.